Good afternoon, everyone. I'm here to talk about MLPerf. First, a quick quiz. Who's heard of MLPerf? OK, it was in the prior presentation, so I'm hoping to see a lot of hands when I ask that. But for those of you who didn't raise your hand, the first question worth answering is, what is MLPerf? MLPerf is a performance benchmarking effort with wide industry and academic support. And when I say wide, I mean we're up to about 65 supporting companies, researchers from 8 different educational institutions. This is the work of a lot of people, both developing the benchmarks, submitting results, curating the various processes. It wouldn't be possible without these folks and many others. MLPerf supports 2 benchmark suites. The first is MLPerf Training, which measures the performance of training systems. The second is MLPerf Inference, which measures the performance of systems doing inference. Except we've just picked up a third, which is MLPerf Mobile. That's essentially inference for mobile devices. So that's what MLPerf is. It measures ML performance. How does it do that exactly? MLPerf Training measures the time to train a model. And we need a clear definition of this. So when I say train a model, what I mean is take a data set, run it through some model, until that model reaches a target quality. For instance, take ImageNet, run it through ResNet until it hits 75.9. How long did that take? So why do we use this time to train metric for the benchmark? Well, first of all, it measures real user value. This is very important to us. This is a real task that someone might do. We're not trying to estimate or guess how the system would perform for a real task. We are measuring a real task. The obvious alternative to time to train is throughput. But you can increase throughput at the cost of time to train. For instance, use lower precision, your throughput goes up, but your time to train may go down. Or, excuse me, your throughput goes up, and your time to train may go up with it. So that's why we use a time to train metric. Another big question MLPerf Training has to answer is, do you specify the model? If you specify the model, then you enable apples-to-apples comparisons of different systems because they're doing the same workload. If you don't specify the model, you enable more innovative approaches with hardware-software co-design, where people come up with new models that are suited to particular systems. We like to have our cake and eat it too, so we introduced 2 divisions: a closed division in which the model is specified, and an open division in which it is not. Closed division tends to be heavily used by chip vendors. The open division is more appealing to people showing off new capabilities or new algorithms. We launched MLPerf Training with these 7 benchmarks, covering vision quite heavily, language, commerce, and research. We tried to choose a good mix of benchmarks that covered most of the common ML primitives, that were at a reasonable maturity point where they were still relevant, but hadn't been published yesterday. Let's talk about MLPerf Inference, on the other hand. MLPerf Inference measures rate of inference. What does that mean? It means, roughly, take inputs, push them through a trained model, make sure that the model is performing with a required level of accuracy. For instance, push images through ResNet, make sure it properly identifies cats. Again, we have a closed division and an open division. Same reasoning. But inference is used in a lot more diverse situations. So we introduced 4 scenarios to handle these different use cases. The first scenario is the single stream scenario. In the single stream scenario, as soon as you finish processing one data item, the next one arrives. This is very similar to what you might see on a cell phone, where you're doing some sort of augmented vision application. Next scenario is multi-stream. Several different streams of synchronized data items arrive. This is very similar to what you see in a multi-camera driving assistance type application. The third is server. Data items arrive according to some sort of Poisson distribution. This is what you might see in, for instance, a popular web translation app. The fourth is offline. All the data arrives all at once, and you process it as quickly as you can. For instance, some sort of photo sorting app. For each of these scenarios, we have a different metric. For single stream, we measure latency, because it's all about speed. For multi-stream, we have a latency bound, and then we see how many streams you can handle given that latency bound. For server, we also have a latency bound, and we measure what kind of QPS you can handle given that latency bound. And for offline, it's all about bulk, so we measure throughput. So that is the inference benchmark, which brings us to which benchmarks we chose. Because of this diversity of scenarios, the number of things we were actually measuring is the number of benchmarks multiplied by the number of scenarios. So we chose a handful to start with: 2 lightweight image tasks, 2 heavyweight image tasks, and a basic language task. And then we're evolving this suite over time. That brings us to question number 3. Does ML performance benchmarking matter? We've got all these people, we're doing all this work, we're producing lots of numbers. Is it worth it? So there's a couple of ways we can assess this. One is to take advantage of the fact that we now have 2 rounds of training results and compare those rounds and see whether we're seeing progress. So what we do is we look at the fastest 16-chip entry to MLPerf training v5 and v.6. These entries are separated by a little over 6 months. They're on the same hardware platforms. They have higher quality targets to meet, which means v06 entries are actually doing more work. Despite this, we see roughly a 30% speed improvement. Same hardware, more work, 30% faster. Now, some of this is obviously because people are getting better at optimizing for the benchmark. But a significant fraction of it is because people are making their software stacks better. We know this through anecdotal evidence from folks working on things like cuDNN and TensorFlow, that a lot of the changes that enable this speed up get pushed into the software stack where they become available to the full range of users. Another thing that I think MLPerf helps to drive is scaling. For training, if you want the best score, using a bigger system is usually helpful if you can figure out how to take advantage of that scale. And what we see between v5 and v6 is that the fastest period drag race submission is using a larger and larger system. And the reason we are able to use those larger systems is because we are getting better at scaling. Again, this is roughly a little over 6 months, same hardware platform. So we're not changing the hardware, we're just getting better at building software stacks that scale. MLPerf Inference, we only have 1 data point, so we can't do the same kind of comparisons, but what we can look at is scope. MLPerf Inference, the first round garnered almost 600 entries from 14 different companies across a wide range of platform scales. So if we look at that benchmark cross scenario space, we can see that the performance range is roughly 4 orders of magnitude. So we believe because of this scope, MLPerf Inference has the potential to drive even more broad progress than MLPerf training. We're excited to see what the next round brings. Another way that we can assess this is are we increasing market transparency? Because it's good to be making people optimize their systems better, but it's also good to help people understand what a well-optimized system is better. So one way we can get a feel for this is to look at press mentions. So MLPerf appears quite a bit in the tech press. We've also been in the Wall Street Journal and The Economist. I think we are giving people a much better way to understand ML performance. And I think this matters because ML hardware is projected to be a $60 billion industry in 2025. That's a lot of money. That's a lot of R&D money. And we'd like that R&D money to be spent wisely and drive real progress. And as Peter Drucker said, what gets measured gets improved. Benchmarking has this almost magical property in that it aligns everyone. It aligns research with development. It aligns engineering with marketing. It even aligns competitors across an industry in pursuit of the same clear objectives. So things are going pretty well, but with MLPerf, we really do take cultural imperatives to both be open and agile, to be aware of where we can be doing better and to get better, importantly. So what are we doing in 2020? So the basics. We are trying to get to a faster and more consistent cadence. Our release schedule earlier has been somewhat unpredictable. And we're trying to get to a basic quarterly cadence, alternating between training and inference. So training in Q1, inference in Q2, training in Q3, inference in Q4. We're driving under the schedule this year, so our schedule is a little compressed, but this is where we would like to get to. We need a somewhat longer schedule because MLPerf does evolve its benchmarks between rounds, and we do have a fairly lengthy peer review process between submission and publication. We're also trying to evolve the benchmark suite to give both better and fuller coverage of the ML space. So looking at things we might want to benchmark, you can see a wide variety of vision tasks: image classification, object detection, image segmentation, 3D segmentation for medical imaging, speech, which is an area we didn't touch in 06, language, both translation and NLP, recommendation at scale, and reinforcement learning. So here's what's going on in training. The green cells are the cells that we have already. In 07, we're adding the yellow cells, which is BERT, which is a very popular and important model these days, and DLRM, which is an industrial scale recommendation benchmark. In 08, we are planning to add a 3D segmentation medical imaging benchmark, TBD, and the RNNT speech-to-text benchmark. Inference is catching up with training. Because we have the mobile suite, we moved some pieces of inference out into mobile, and now we're filling in the rest to align it with training. So in 07, we'll add BERT, we'll add DLRM. Inference 07 is a little later, so it can pick up RNNT. And then in the next version, we'll also look at 3D segmentation and translation. Mobile is just launching with 07. And the tasks that it's looking at thus far are the sort of three basic vision tasks, speech-to-text, and NLP, which should be a fairly broad sweep over what one might like to do with a ML-enabled cell phone. We do have some challenges in 2020. These are things that both we've become aware of through introspection, and things that have been raised by the press or by other companies. We really do try and figure out where the opportunities are and address them. One of the things we want to do is make sure we're evolving the benchmark suites fairly, that we're choosing the right benchmarks. Another thing that we want to do is provide better efficiency information so that people can say perf per unit something. A third is to reduce our results sparsity. We allow people to submit subsets of the benchmarks, and this can lead to sparse results. And a fourth is to try and reduce the cost of submitting to the benchmark. We'd like as many people as possible to submit. So let's dive on each of these briefly. How do we evolve a benchmark suite fairly? What does fair mean? Well, what we think it means is you choose benchmarks that reflect the most impactful industry and research needs. You want to move the industry and research field as rapidly as possible in the areas that matter. So what does that mean? What is most impactful? Well, the approach we've come up with is we convene advisory boards of 3 to 5 industry users and 3 to 5 academics, and we ask them. And usually we can get them to produce a reasonable consensus, and this gives us a good direction. So far, we've been able to take this approach with our recommendation benchmark and the medical image benchmark we're working on. And we're in the process of setting up advisory boards for automotive and speech. In particular, for speech, the people who are in-speech users, meaning they want to buy hardware to do speech things, tend to be secretive about exactly what they do and how they do it. And we really could use a few industrial advisors to at least share a little bit of the direction they think is important. So if you are a speechifying sort, or you know a speechifying sort, please encourage them to reach out. The next one is improving efficiency information. So here's the problem in a nutshell. I show you two systems, foo and bar. I show you them for offline inference. That is, just run inference as fast as possible for ResNet. One of them posts 800 images per second. The other one posts 1,000 images per second. So bar is better, right? Clearly better. That's the system. Except I then show you chip count. And so clearly foo is better, right? They get 800 with one. That's 800 per chip versus 250 per chip for bar. Then I show you power, right? That's a heck of a chip. By the way, Cerebras ruined this whole chip count thing for everyone. All right, so we really need to provide good information here so people can get a feel for efficiency. Because inference in particular is infinitely scalable. You want a better MLPerf inference score? Right now, run more hardware. Right now, the only efficiency information we provide is number of chips. And as this example shows, it's crude, but it's better than nothing. What we'd really like to have is power. We're working on that now. We're going to try and at least make that optional in the next round. Maybe cloud cost, maybe other things. I don't know. Chip area, weight. If you have ideas on how we can fairly and usefully measure efficiency, please reach out. This is not a simple thing to do. Third thing we'd like to try and figure out how to do is reduce result sparsity. Here's the problem in a nutshell. Two chips, like to be able to compare them. One submitted benchmark X, the other submitted benchmark Y. That's not great. Why do we allow sparse results? We do it because some people want to build specialized chips. Benchmark X may be the only thing chipmaker A cares about, and benchmark Y may be the only thing chipmaker B cares about. And we also need to enable vendors, especially smaller vendors, to focus their investment. Asking them to do the entire suite when, for our ML benchmarks, we presently enable and practically require people to re-implement the benchmarks for their system is an expensive engineering investment, and people right now need to be able to focus that on the things that matter most to their customers. So that's why we have sparse results. We'd like to figure out how to make them denser. Some things we're looking at. For inference, we have that full benchmarks by scenarios cross-product, but you can probably figure out that people don't want to run recommendation on their cell phones. So we probably don't need a single stream recommendation scenario. So we can prune this space. Another thing that we could do is make a small number of benchmarks required. You can submit these two, and then you submit whatever else you want. And that would at least give us a few dense verticals. This runs into the specialized chip problem, though. So we're talking about this. We're trying to figure out an approach for addressing it. The fourth thing we're trying to figure out how to do is reduce benchmarking cost. It's worth talking about why good ML benchmarking is relatively expensive. The first thing is we benchmark real user value. If you want to benchmark, do a synthetic benchmark, it's very cheap to produce bad results. We've had some synthetic performance benchmarks in the past. They have not been good experiments. If we were to deviate from this, Dave Patterson would appear in a puff of smoke and club us all over the head with a copy of Computer Architecture: A Quantitative Approach. We'd like to avoid that clubbing. The second reason it's expensive is because of software stack and system diversity. Right now, there are several different software stacks people can choose from. Systems have a wide range of scale and implementation approaches. If we nail down a particular source code or a particular binary, we run the risk of targeting certain systems for which that is good and being unfair to systems for which it is not. And so right now, we do allow people to re-implement benchmarks subject to a definition of equivalent functionality. But this re-implementation is time-consuming. It requires ML engineers, which are scarce, doing some pretty hard work. The third reason it's expensive is time to train is a high variance metric. And if you want to measure it with reasonably low error, you need multiple runs. And this just chews up more system resources. So what ways could we reduce these costs? So one of the things we are discussing is doing an out-of-the-box code division. So this is the sort of classic benchmarking where here's the source code, run it, it gives you a number. This might have limited applicability, but for some people, this might be the right trade-off. And as long as we're comparing only people running out-of-the-box code who've opted in, maybe that's a reasonable thing to do. Or maybe we could make it 95% out of the box with a small number of tunable areas that tailor it to systems. Another thing we're talking about is for training, could we do something where we do enough benchmark characterization that we can either normalize away some of the variance mathematically, or maybe even estimate convergence from shorter runs. These might be ways to reduce the system costs. And lastly, we can improve our reference code and best practices, just make it easier for people to get off the ground. So this is an important thing to address. We really do want everybody who has an ML chip to be able to benchmark it with MLPerf. We'd like to make that happen. And we're working hard. Good ML benchmarking is a difficult thing to do. And we really like to get smart people involved. So if you have ideas on how we can address these problems or make it better, please join an MLPerf working group. We'd love to have you. The fifth question, to go broad, is how can we make ML better beyond benchmarking? We've assembled a pretty impressive group of people to build MLPerf, and we'd really like to see what else we can do to make our collective industry and field a better place. So we are creating a nonprofit called ML Commons with a mission to accelerate ML innovation. One of the things ML Commons will do is host MLPerf. But we'd like it to do some other things. Because we believe there's a recipe for accelerated innovation. You take precision measurement, also known as benchmarks. You take good raw materials, also known as large public data sets. Combine it with state-of-the-art manufacturing practices, also known as best practices in the software world. And some motivating examples of what it can do, perhaps through research challenges or similar outreach. And you get a rapidly growing industry. We have seen this before. It is a good recipe for everybody involved, and we'd like to do what we can to help put the ingredients together. So this all sounds good, but how do you make it concrete? I'm going to give you two concrete examples of things we've already started working on while we do the legal bring up for the nonprofit. One of these is a best practice called MoBox. The idea here is basically we'd like a lightweight way to share models for benchmarking our experiments. This is not for deployment. This is not a lifecycle management tool. This is just, hey, I've got some code for the next BERT, right? I'd like to share it with you. I'd like you to be able to get it up and run it as quickly and easily as possible. Right now, generally, when we try and take some code, say for a new reference benchmark, and give it to someone else in another company, that's 2 engineering days before they're able to run it as well, just as a rough estimate. We'd like to take that friction out of the system. So our basic idea is we should have a really lightweight spec for a Docker with a standard file system-based interface. Something like this. You have an MLBox. It takes some data sets. It takes hyperparameters in a file with a specified format, so you can give them to your friends. It gives you a platform spec, so you know what it can run on, and you can tell it what instance of the type of platforms it can run on to use. And it does useful things for you. It produces trained models, or produces inference outputs, or produces logs. The details here aren't really important. What is important is the idea. We're really trying to make the shipping container of ML models. So if you think about a shipping container, it's just a metal box with known dimensions. That's all it is. But some amazingly complex things are enabled by those known dimensions. ranging from ports that process an amazing amount of cargo every day to the entire train network, to interstate trucking, to massive cargo ships. Right? They all just depend on a very simple set of dimensions. And we think that something like MLBox could enable other people to build far more complex things using a very simple spec. Another thing that we're working on is our first attempt at a large public data set, which we call people's speech. This is a great effort being led by Greg Diamos at Landing.ai. Why do we think this is an important thing to do? Public data sets fuel innovation. 80% of papers from large tech companies, these are Facebook's, Google's, companies that have great data, cite public data sets. Because that is how you prove the benefits of your ideas to the world in a way that you can share. And our public data sets, to be frank, are not great. They've gotten us here, but if we want to take it to the next level, we need better ones. So what do we want to do with people's speech? We'd really like to create 100,000 plus hours of transcribed speech in diverse languages by diverse speakers with a public use license. It is frustrating that every time you want to touch a data set, you have to go have an uncomfortable conversation with legal. Another quick quiz. Raise your hand if you like having data set conversations with legal. OK. So why speech in particular? Smart speakers and assistants are expected to reach the entire Earth's population by 2025. The world has over 1,000 languages with 1 million speakers. Here's a great illustration of all that linguistic diversity. To sum up our current state, I think Greg Diamos has a great story. He says, at home, I have a smart speaker. And it understands me just fine, but I'm a white male. My wife has a slight Indian accent and has a real hard time following her commands. And this is not a good situation. And you can observe that our speech data set of choice right now is LibreSpeech, which is recordings of the European Parliament. And you can pretty much guess the demographic that represents. So we'd like to make a large, publicly available, more diverse data set. We think this would move the whole field forward. So those are the kind of things we want to work on with ML Commons. Bonus question. How do you get involved? If you think these are interesting things, you'd like to be a part of them, that would be awesome. Please reach out. MLPerf.org, get involved, or info@mlperf.org. Both good ways. We'd love to hear from you. Thank you, everyone, for listening. Questions?
I have a question. Why do you, I'm right over here, why do you think the community hasn't moved on past ResNet 50 yet?
That's a very good question. I think there's a couple of reasons. One is there is something nice about the long historical baseline it has, where you can sort of track the increase of performance over years. Another is it still has a pattern of operations that is representative of a lot of different image models. They're not that different. The third is, we haven't really had a benchmarking organization until fairly recently. And so people have to look at what the last paper did, right? That's what you benchmark. And so this is an ongoing discussion inside MLPerf, which, we're a very open organization. We'd like to have people join this discussion. When should we move on from ResNet? And if we do move on, what do we move on to?
Yeah, so that's something I'm trying, I'll talk to you about later.
Sounds good.
All right, let's thank Peter one more time.